Oh my goodness.
It's going to be okay. All right. So the first section in our applications of derivatives chapter is called related rates. Right? In this section, we're going to take a look at a lot of, it's mostly geometric problems, okay, with different things changing with respect to time. Okay? For example, we could have, if we're throwing pebbles into a pond, right, we can talk about the ripples and how quickly the ripples are changing, how fast the area is changing with respect to the change of the radius, those types of changes. Okay? So the first thing that we want to do is just talk about the notation that goes along with this. All right, so these different scenarios here, like the volume of the cylinder is increasing or the depth of water in a rectangular pool is decreasing. Whenever I'm talking about a rate, okay, a rate is a derivative. Right? Rate is how much something is changing. That's what a derivative is. A derivative is how quickly something is changing. It's the slope. So whenever we see a rate, we want to think derivative. Okay? Rate means derivative. So our notation for this first one, if it says the volume of a cylinder is increasing at a rate of 6 cubic feet per second, the way I'm going to express this rate, and I'm going to say that my volume, right, is my original function. Well, if I take the rate of change of the volume, I'm going to express it like this. Okay? Everything that we do in this section is going to be with respect to time. So that's where this t comes from. Right? This is the change in volume with respect to the change in time. Okay? That's what this dv over dt is saying. It's the same idea as dy over dx, right? But we're going to make our notation specific to whatever we're talking about in the problem. So we're saying the rate of change of the volume with respect to time is equal to 6 cubic feet per second. Okay, the rate of change of the volume, dv dt, is equal to 6. So in the second one, we have the depth of water in a rectangular pool. Right? So here, if we're talking about depth, I mean, that's another way to say that is the height of the water. Right? We're thinking about a rectangular prism. So, I mean, you could write dd over dt for the change in depth, but personally, I think it makes more sense to write the change in height with respect to time in this case. And I mean, it wouldn't be wrong if we wrote dd over dt. I mean, we're defining these variables ourselves. Right? We're saying that this is the change in the height with respect to time, and this is just equal to 2 inches per hour. Less. So, how about number 3 here? The number of vehicles going through the toll booth is increasing at a rate of 85 vehicles per hour. How could I express that using this notation? Something over dt, yeah. What could I put over dt? Yeah, right, it's just the rate of change of the vehicle. So, I mean, we could say dv over dt, right? The rate of change of the number of vehicles is equal to 85 vehicles per hour. Right? How about number 4? So here, if we think about our units, we're talking about cubic centimeters, so that would be the volume, right? So we want to say the rate of change of the volume. So dv over dt is equal to 15 cubic centimeters per second. All right, now with these, there's one extra thing that I want to go back and look at. If our rate is increasing, it's going to be positive. If our rate is decreasing, we should make our rate of change negative. Right? So that's another important thing that we have to check in all of these problems. Okay, number 3 was increasing. Therefore, our rate should be positive, our rate of change. And number 4, increasing or decreasing doesn't show up, but escaping does. Right? That means decreasing. That means going down. So here our rate should be negative 15 cubic centimeters per second. Okay so far? Just expressing rates using our calculus notation. All right, so the other thing that we need to look at before we actually start getting into problems is taking derivatives of a lot of these common geometric formulas. Right? I'm pretty sure every related rates problem I've ever seen on an AP test involves one of these formulas. Okay? It's 99% of the time it's a geometric problem. Right? So when we are doing these problems, what we're going to have to do is take derivatives of these geometric formulas. Now what we're going to do is treat every variable, or we're going to take the derivative of every variable with respect to time. What that means is every single variable has to be implicitly differentiated. Okay? So what that looks like, I'll do a couple examples here. So here, this is 2 separate variables, right? L and W. Yeah, we're going to do it to all of them. We're treating every single one as its own function. Right? We're saying that every single variable is changing with respect to time. Right? So, for example, if we're talking about the area of a rectangle, right, I might say that the rectangle is increasing, right? The length and the width are both increasing with respect to time, therefore the area is also increasing with respect to time. So I need to treat each variable as its own function. So when I take the derivative, I'm thinking, well, I have to use product rule here, right, on this side. If I take the derivative of A, I just get dA dt, right? That's its own function. So the derivative of A is dA dt. But then over here, if I'm using product rule, I'm saying, well, the derivative of the first, so the derivative of L, would be dL dt times the second, so times W, plus the first times the derivative of the second. Okay? I'm treating every single variable as its own function that I have to implicitly differentiate. So every single variable is going to have one of these tacked on, right, when I take the derivative. Right? Just like when we implicitly differentiated for y, every time we solve y, we had to tack on a dy dx. Here, we're doing that for every single variable. Okay? So here, for the circumference of a circle, I actually only have 2 variables, right? 2 things that would be changing, my c and my r. 2 pi is just a number. That's not a variable. That's not going to change. So when I take my derivative here, I will have dc dt equals 2 pi, 2 pi dr dt. What's that? So how about number 7, the volume of a cube? What would this derivative look like? dv dt equals right, so we'd still have 3s squared, then times ds dt. Right? about surface area of a cylinder? How many different variables do I have here? 3, right? We've got S, R, and H. So, right, so we're going to have to do the product rule for the right side here. So we can think about 2 pi r as one function, and then we can think about H as my other function over here. So what's that going to look like? Wait, say that again?
Oh. Pi r. Ah.
Yeah. Alright, so here, 2 pi dr dt is my derivative of 2 pi r times h plus 2 pi r times the derivative of h. So one of the most common things that shows up on the AP test is volume of a cylinder or volume of a cone. It could be something like we are pouring water into a cylindrical or a conical vessel. How fast is the volume of the water changing when the radius is 5? Something like that. So every single question I've seen on the AP test that involves volume of a cylinder or volume of a cone, they give you the formula within the problem. You are expected to know things like area of a circle, circumference of a circle, area of a rectangle. Like, they won't give you those if the question deals with that, but they will give you these volume formulas. Alright? And that's not on a formula sheet or anything, that's just in the problem itself. It's like, remember the volume of a cylinder is pi r squared h, right, to do the problem. So, do you guys think you can take a couple of minutes and try to find the derivatives of the rest of these here? I didn't ask if you wanted to, I asked if you could. 10?
No, 11.
Oh,
Or
that's
is that an R?
that's an R.
Okay.
Yeah.
Is it R squared?
Your R's do look like S's because that one has a tail as an O.
This one?
Yeah. I'm not saying it's bad, it's just a different writing style.
You could say my handwriting sucks. It's okay.
Dude, your handwriting is better than mine.
How do you get 4, 5?
So I brought the 3 down. So 3 times 4 thirds would just be 4. So you want me to show you real quick?
Yeah, please. I'm really very helpful.
So 3 times 4 thirds. And there's 2 ways we can think about this. One is if I just multiply straight across, I get 12 over 3, which is 4. Or, before we do that, I'm allowed to cancel out common factors. Okay?
You should know how to add fractions real quick.
Sure.
I'm so sorry that I don't know how to do this, but
Like 1/2 plus 1/3.
Yeah.
So I need common denominators. To get common denominators, the easiest thing to do is just take this one and multiply by whatever this denominator is. So times 3 over 3. I'm allowed to do that because this is 1. That doesn't change the value. Right? So then over here, same thing. I would multiply by this denominator. So I get 3 over 6 plus 2 over 6. Now once I have common denominators, I just add the numerators. 5 over 6. Alright. Do we feel okay with this? Fine? Oh, I forgot my DBDT, didn't I? I just wrote B. There we go. Catch. Alright, any other questions on this before we take a look at what problems would actually look like with this stuff? We're just going to do a few simple ones. We're not going to look at anything that would be on the AP test. Just some simple ones. They actually, we'll get into more complicated ones. But the ones we're going to do today are pretty straightforward. Well,
just want to go back
I have a question. Why don't you have one of your smart like at home? Like
I do. I just think it's easier to write with a regular marker. I'm an old man already. Rebelling against technology.
no. I'd rather have all use dry erase markers, like use the thing, and it's like stop because I can't read it.
Yeah, my handwriting is bad enough already. Like, I don't want to mess with
No,
it.
he just now he picks a good color. Like he likes to change colors, so you have like yellow and like green, and it's like you can't see the yellow or green, so it's like
Alright, so we've already talked a little bit about this stuff up here in the top, but let's go over this real quick before we jump down and take a look at a couple of problems. So the derivative of a function, okay, is the rate of change. Right? That's pretty much what we've been talking about all of calculus. Right? Derivative of a function is its instantaneous rate of change. So what we're going to start doing, right, is applying that idea to these related rates. This idea we're actually going to talk a lot about more in the next section, right, when we talk about position, velocity, and acceleration. Okay, but when a function describes position or distance, the rate of change, its derivative, is its velocity. Okay, how quick the position is changing. Right? So down here, right, a rate of change answers the question how fast something is changing. Right? How fast a quantity is changing, how fast the area is changing, how fast the volume is changing, something like that. Okay? So, for example, we say if we're talking about the rate of change of a volume, we label that dV dt. That's what we talked about already. And then these two here, okay, we mentioned this as well. Whenever we have something, some rate decreasing, the rate is negative. Right? Whenever the rate is increasing, it's positive. Okay? And the example that they give here is if I'm walking towards a lamppost, the distance between the lamppost and myself is decreasing, so I would make that a negative rate of change. If I'm walking away from the lamppost, then my distance is increasing, so that would be positive. Okay. So the guidelines here, we're going to kind of go through these as we do the first problem together. And we're actually just going to skip to number 2 because example 1 doesn't really follow those guidelines.
It's all right.
She paid attention to what's going on. I can pay attention all I want. The one day I guess you wouldn't know unless you tried.
Well, on that test, there were just a couple of tiny mistakes. You're talking about that quiz, right?
Yeah, I thought it was. No.
Alright, so this first example, we've got a pebble dropped into a pond. And it causes ripples, okay, that form concentric circles as they expand. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, what rate is the total area of the disturbed water changing? So, the first thing that we need to do is figure out what geometric formula is going to relate everything we're talking about in this problem. Okay? So, what are we talking about here? A pebble. Okay. So what's happening with that pebble?
It's getting tossed into the water. I'm guessing
Form of concentric circles.
So what geometric formula would relate this information?
circumference.
Area of a circle, right? Okay, we're talking about the area of a circle here. So what we're going to write for our no is our formula that relates everything we're talking about. Right? This is just area of a circle. Then let's take a look at what we're given in this problem. Okay? We are told that the radius of the outer ripple is increasing at a rate of 1 foot per second. Okay? We are given a rate at which something is changing. We're told that the radius is changing at a rate of 1 foot per second. So the dr dt, the rate at which the radius is changing, is 1. Right? What else, Mike? So we want to figure out what's going on at the instant when r equals 4, okay, when the radius is 4 feet. So what I want to do then, okay, my goal is to find the rate at which the area is changing. So what I want to find is dA dt at the instant when r equals 4. So what we want to do is take the derivative of our function, and then we'll just plug in what we know. So how do I take the derivative of a equals pi r squared? Yeah, I mean, the way you said it's fine. Pi times 2r. Yeah, I mean, I just pulled the 2 out front. So I want to find dA dt. I have r and I have dr dt. So I'm just going to plug those two pieces of information in. So dA dt, 2 times pi times 4 feet times 1 foot per second. I like to write in the units as well, just so we make sure that we get our units of our final answer correct. Right? So when I multiply all this out, 2 pi times 4 times 1 would just be 8 pi, right? So then what would my units be here? Feet squared per second, right? And we're talking about the rate of change of the area, so hopefully that makes sense. We're talking about square feet per second. And that's why I like to write in the units here, just to make sure that we get that final unit correct. All right. And that's our answer. The rate of change of the area is 8 pi feet squared per second when the radius is 4. Come on, that wasn't that bad. All right. Feel okay with that one? Yes. All right, let's take a look at example 3. One day, yes.
And the near future. We need a time machine.
Time machine?
Yeah.
What?
You just skip it. No, you should enough. You're smart. You're welcome.
All right, so in example 3, air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon changing at the instant the radius is 30 centimeters? Right, so our spherical balloon is just increasing in size, right? So what formula would relate this information?
Oh, you want to steer.
Oh, that's like that's
Right. Yeah, so we want volume of a sphere. What is volume of a sphere?
V equals 4 divided by 3 pi r.
4/3 pi r cubed. It's on the other sheet. Alright, so this one, again, is probably one that you would be given in an actual AP problem. Okay? If you need to work with the volume of a sphere, you would probably be given this formula. Okay? So then what do I know in this problem? Alright, so the air is being pumped in at a rate of 800 cubic centimeters per minute. So how would I express that?
dV T equals 800 over 1 minute.
Yeah. The rate of change of the volume of this balloon is 800 cubic centimeters
That
per
is
minute.
my hoodie.
So, what do we want to find then?
Oh, any radius is.
Yeah, So we want to find the rate of change of the radius at the instant when r equals 30. So, what should I do? Find the derivative. So what would my derivative here of volume of the sphere be? And now I know dv dt, and I know r, so I can plug both of those things in and solve for dr dt. So dv dt is 800 times 4 pi times 30 squared. Right. And we would just need to get dr dt by itself. Do I need to mark it up?
Wait, are we halfway there?
I think we're more than halfway there.
Oh yeah, we're
What was our goal?
1, 2, 3, 4,
100.
5, 6.
Yeah, I was kind of wondering that from the beginning.
I think our goal is just to see how many times we say it. I don't know because they want to figure it out.
When we get to 100, he takes his hair to
Yeah.
It's 67.
It should be like if you don't get to 100, then I take my hair down.
I feel like you should take her down.
Right.
That's weird. Our Christmas gift from you. See, Diana always says things like, she said that she just like whispers it to us, and she's like, I can't wait for someone to like say it for me. She makes it, yeah. I know. She'll be sitting here next to me. I'm not kidding. She'll be sitting next to me, and he'll be like, "What's this?" And then she says it, and then she says it again. She says it 15 million times, and just whispers it in my ear. Then I finally say it, and you're like, "Yeah." And I'm just like, "Why can't you speak for yourself?" I'm afraid that if it's wrong, everybody will know that I'm actually wrong. No, my favorite game is. I got 36 on the ACT. I've been saying it.
No stabbing.
Oh,
I don't think anyone.
he said that before.
It sounded the time before. I did not know how to add. I did not know how to add fractions about 30 minutes ago.
But now you do.
We all have room to grow.
Thank you. That was a little.
I'm done.
Alright,
I need
so
at least
how do I finish this one out? How do I solve for dr dt?
Divide by
so I can
4
drop the
pi.
cover.
I guess I should have put in my units here.
Just a little bit.
800.
See, this looks too much like chem. I want to cry.
And
Wait, what? Can you match? No,
By
I
the
can't.
way, is this on the calculated portion?
this would probably be fair game to not be on the calculator portion.
What?
I mean, you should be able to do 30 squared.
No, it.
What is 30?
And
It should be like 900.
So what we have here is 800 cubic centimeters per minute is equal to, so that we got 900 times 4.
3,200. What? 28. I'm sorry.
So we did 30 squared. It's 900. 900 times 4. 3,600. So we've got 3,600 pi. No, wait, what would my units be then? Centimeters squared. Times dr dt. Now we divide. Right? We'll divide both sides
So
by.
it'd be 2 divided by 9.
So I'm going to divide both sides by 3,600 pi centimeters squared. So come back up here then. So we have 800 over 3,600. How could I reduce that?
2 divided by 9.
Yeah. 2 over 9, right? So 2 over 9 pi. What would my units be? Centimeters per minute, right? So the rate of change of the radius at the instant when the radius equals 30 is 2/9 centimeters per minute.
Run out of it.
See, when I tried to do this by myself, I got like over 2 million.
You end up multiplying 800 times 3600 pi instead.
Maybe.
Alright, how do we feel?
No.
Not good.
No, it's just that's what I always start off with. It really looks like chemistry. I'm not joking.
Just because the units thing?
All of it.